Hello all, welcome to my lecture on interrupts which comes under module 3. We have been discussing about various synchronization techniques, and in the previous lecture we have discussed about program controlled IO where the processor itself need to check the status of each of the input output devices connected to it, and the main drawback of it is wastage of time. The second technique, that means interrupt, can overcome this drawback, and the processor can perform other tasks while waiting for an IO device to become ready. That means the processor need not worry about the status of input output devices connected to it. This can be done by arranging the input output device to alert the processor whenever it is ready. And the input output device do this by sending a hardware signal, which we call it as interrupt, to the processor when it get ready. To achieve this, one of the best control line called an interrupt request line is used, and thus the waiting time of processor can be eliminated. Next is transfer of control through the use of interrupts. Here you can see two programs, program 1 a compute routine, program 2 a print routine. Compute routine is having m number of instruction, and on executing the ith instruction it encounters an interrupt and it transfers the control to the print routine. There it executes all the instructions in print routine, and after completing it transfer the control back to the compute routine, that means to the i+1th instruction. The routine that is executed in response to an interrupt request can be called as interrupt service routine. Here in our example, the interrupt service routine is print routine. When an interrupt request arrives during the execution of instruction I, first it completes the execution of current instruction, that is I. Then current contents of PC, that means on executing the ith instruction, the program counter value will point to i+1th instruction. That value must be saved in some temporary storage. Then loads the program counter with the address of the first instruction of the interrupt service routine. Then after executing the interrupt service routine, it loads the program counter with the address of the i+1th instruction to resume the execution of compute program or compute routine. The two terms related to interrupts are interrupt acknowledged signal and interrupt latency. Interrupt acknowledged signal is issued by the processor. Suppose a device requested or raised an interrupt request and the processor accepted it and started executing the corresponding interrupt service routine. So the processor must inform the requested device that its request has been recognized, and the device must remove the request signal. The signal which is used for this purpose is called as interrupt acknowledge signal. Then interrupt latency is the delay between the time an interrupt request is received and the start of execution of interrupt service routine. Next is interrupt hardware. In a system having a processor and n number of input output devices, a single interrupt line may be used to serve n number of devices. That means for all the n devices, a single interrupt line can be used. Such a type of organization is shown in this diagram. Here you can see a processor and n number of input-output devices. All are connected to a common interrupt request line INTR through a switch. To request an interrupt, a device closes its associated switch. If all interrupt request signals INTR1 to INTR-N are inactive, the voltage on the interrupt request line will be equal to VDD. That means there is no voltage drop across the line since all the switches are open, and it indicates the inactive state of the line. When a device requests an interrupt, it closes its switch, which result in the voltage drop across the line. That means the voltage drops to 0, which causes the interrupt request signal INTR received by the processor to go to 1. Here, more than one device can request interrupt at the same time, which causes the line voltage to drop to 0. Hence, the value of INTR is the logical hour of the request from individual devices. That is, interrupt request line INTR equal to INTR1 plus INTR2 plus up to INTR-N. Next is enabling and disabling of interrupt. Suppose a device requested an interrupt, then the processor accepted it and started execution of corresponding interrupt service routine. But the device doesn't remove its request signal during the execution of corresponding interrupt service routine, and this causes a problem that the processor may misinterpret this signal as another interrupt and go on servicing the request, and which may lead to successive interruptions and causing the system to enter an infinite loop from which the system cannot recover. We have three important solutions for this problem. First solution is the processor hardware ignore the interrupt request line until the execution of first instruction of the interrupt service routine has been completed. That means a device requested an interrupt and the processor accepted it and started execution of corresponding interrupt service routine until the completion of execution of first instruction of interrupt service routine. The processor ignores the interrupt request line in order to prevent further interrupts, and as the first instruction it puts the interrupt disable instruction. Then after completing this interrupt service routine, other interrupts must be received by the processor. Hence, as the last instruction of the interrupt service routine, an interrupt enable instruction should be attached. This is the first solution. Here, interrupts are enabled and disabled by using instructions. The second solution is the processor automatically disable interrupts before starting the execution of interrupt service routine. Here the interrupt enable bit of processor stack register, that is PS register, indicates whether the interrupts are enabled. That means in the processor stack register of the processor, there is a bit called as interrupt enable bit. If that bit is set to 1, it indicates that interrupts are accepted, and if that bit is set to 0, it indicates that the processor ignores all the interrupts. Before accepting any of the interrupt request, the value of this interrupt enable bit of PS register will be 1. If the processor accepts any of the request, first it need to save the current status of PS register onto the stack, and in that PS register, that interrupt enable bit is set to 1, and after saving the PS register to the stack, the processor need to load the PS register to execute interrupt service routine corresponding to the current interrupt. In that PS register, interrupt enable bit is set to 0 to ignore interrupts from other devices until completion of the current interrupt service routine. After completion of interrupt service routine, the previous status of PS register must be reloaded, and in that PS register, the interrupt enable bit is set to 1, indicating that the processor is able to accept interrupts. This is the second solution. And the third solution is the processor has a special interrupt request line for which the interrupt handling circuit respond only to the leading edge of the signal. That means edge triggered line. That means once a request from a device, interrupt request from a device is accepted, even if the interrupt request line is kept active during the execution of interrupt service routine, it may not create any misunderstandings to the processor. That means only once it triggers the interrupt request on its leading edge. Hence, the processor will receive only one request regardless of how long the line is activated. This is the third solution. Next is the sequence of events involved in handling an interrupt request from a single device. First, the device raises an interrupt request. Then the processor interrupts the program currently being executed. Then interrupts are disabled by changing the control bits in PS register. That means the interrupt enable bit of PS register is set to 0. Then the device is informed that its request has been recognized, and in response it deactivates the interrupt request signal. Next, the action requested by the interrupt is performed by the interrupt service routine. Then finally the interrupts are enabled and execution of interrupted program is resumed. Next is handling multiple devices. When a device raises an interrupt request, it's set to one of the bits in its status register. That bit is IRQ bits, interrupt request bit. The, in the previous lecture, we have discussed about status register and control register associated with IO operation. In the status register, I have mentioned 4 important flags: S in, S out, KIRQ and DIRQ. S in and S out we have discussed in that lecture, and the flags relevant to interrupt request are KIRQ and DIRQ. That means IRQ flag corresponding to keyboard is KIRQ and IRQ bit corresponding to display device is DIRQ. That means if a keyboard need to raise a request, interrupt request, first it must set this KIRQ bit of its status register to 1, and if the display device need to raise an interrupt request, it must set this DIRQ bit to 1. Now, the way to identify the interrupting device is to have the interrupt service routine poll all the input-output devices connected to the bus. That means the device which need to raise an interrupt request set the corresponding IRQ bit to 1. Now the processor need to identify the devices that requested interrupt service. So the corresponding interrupt service routine polls all the devices that are connected to the processor to check whether it requested an interrupt or not. The first device encountered with this IRQ bit set is the device that should be serviced first. And the disadvantage of this technique is the time spent in interrogating the IRQ bits of all the devices that may not be requesting any services. Here, the interrupt service routine polls each and every input-output device connected to the processor. In that case, sometimes most of the devices may not be requesting any interrupts, and interrogating into the IRQ bits of that devices will be a waste of time. It is a disadvantage of this technique. To reduce the time involved in the polling process, another technique is introduced which is called as vectored interrupt, where a device requesting an interrupt can identify itself to the processor by sending a special code to the processor over the bus. This enables the processor to identify individual devices. That means if a device need to raise an interrupt request, it must send a special code to the processor. On receiving this code, the processor identifies the device that raised the interrupt request, and the code supplied by the device may represent the starting address of interrupt service routine for that device, and the code length ranges from 4 bits to 8 bits. Next is interrupt nesting. During the execution of an interrupt service routine, interrupt requests from high priority device should be accepted, and those requests from devices of same priority or lower must be ignored. Such type of organization is called as multiple level priority organization, and it purely depends on the device's priority. Here a priority level is assigned to the processor that can be changed under program control. The priority level of processor is the priority of the program that is currently being executed by the processor. This disables the interrupts from devices at the same level of priority or lower. And this multiple priority scheme can be implemented by using separate interrupt request and interrupt acknowledge lines for each device. That means each of the devices having two different lines. One is for interrupt request and other is for interrupt acknowledge. Each of the interrupt request line is assigned a different priority level, and the interrupt request received over these lines are sent to a priority arbitration circuit in the processor, and in that circuit it finds the priority of each of the devices, and a request is accepted only if it has a priority level than that currently assigned to the processor. That means if a device need to raise a request, it can do it by using its dedicated interrupt request line, and the processor may receive a number of requests at the same time. So it sends all the requests to another unit called priority arbitration circuit, where it find the priority of the devices, and a request is accepted if the incoming request has higher priority than the priority level currently assigned to the processor. Others are ignored. And this one is the diagrammatic representation. Here you can see the processor. Inside of it is priority arbitration circuit, which is used to find the priority of each of the devices, and you can see p number of devices. Each of the devices having dedicated line for interrupt request and interrupt acknowledge. That means for example, device 1 is having its interrupt line request line as INTR1 and interrupt acknowledge line as INTA1, and so on. Next is the case of simultaneous request. That means it is possible that simultaneous requests can be arrived from two or more devices. Then how to handle this simultaneous request? Which one should be processed first? The first solution is poll the status of IO devices and find the priority of each of the devices. Here the priority is determined by the order in which the devices are polled, and a widely used scheme is daisy chain. A diagrammatic representation of daisy chain is given here. Here you can see a processor and n number of devices. All the devices are connected to a common interrupt request line, and the interrupt acknowledge signal from processor is first passed to device 1 and then from device 1 to device 2, then up to device n. Here the interrupt request line is common to all the devices, and the interrupt acknowledge line is connected in daisy chain fashion. This type of arrangement is called as daisy chain. Then the interrupt acknowledge signal, that is INTA signal, propagate serially through the devices. When several devices raise interrupt request, first the interrupt request line get activated, then the processor responds by setting INTA signal to 1. First this INTA signal is received by the first device connected to the processor. If the device 1 has a pending request for interrupt, it blocks the INTA signal and put its identifying code on the data lines. That means here it uses a vectored interrupt. If the device need to raise an interrupt request or it need to get serviced, it stops the interrupt acknowledge signal and sends the corresponding or sends its special code to the processor. And if does not need any service, it passes the interrupt acknowledge signal to the second device and so on. Here the device that is electrically closest to the processor has the highest priority. Next is solution 2. Here the devices are organized in groups and each group is connected at a different priority level, and within a group devices are connected in daisy chain. Here you can see a processor priority arbitration circuit, and to the processor two groups are connected, an upper group and lower group, and each of this group is having a daisy chain model. If two devices or if devices from different groups request interrupt service, the priority arbitration circuit finds the priority of devices and it passes the interrupt acknowledge signal to the corresponding highest priority group. The first device in that highest priority group receives the interrupt acknowledge signal and then it proceeds like daisy chain technique. That means if that device needs a service, then it blocks the interrupt acknowledge signal and passes its special code to the processor, and if it doesn't need any service, then it simply passes the interrupt acknowledge signal to the second device and so on. This is the second solution and is the popular one also. And finally, controlling device request. And there should be a mechanism to control whether a device is allowed to generate an interrupt request. The interrupt enable bit in devices interface circuit is used for this purpose. For example, here you can see control register. In that you have two important flags DN and KN. KN is the interrupt enable bit corresponding to keyboard and DN is the interrupt enable bit corresponding to display device. Whenever a keyboard device need to raise an interrupt request, it first set the KIRQ bit to 1 and it can only raise a request if the KEN keyboard enable bit of its control register is set to 1. Likewise, for a display device also, even if the DIRQ bit of its status register is set to 1, this DEN bit of control register decides whether the device is able to raise an interrupt request. Only if this enable bit is set to 1, the device can raise a request. And this way the interrupt generation technique can be controlled. And this is all about interrupts, and in the next lecture we can discuss about DMA. Thank you.